Hi folks, welcome back to another live review session. Tonight we're going to be talking about law of sines, law of cosines, and then we're going to get back into those pesky little trig identities and trig equations that some of you may be struggling on. So we're going to get started with law of sines, and basically what does law of sines say? Well, it says if you have angles with the capital A, capital B, and capital C, and then the corresponding sides that are opposite those angles as little a, little b, and little c, what happens? Well, you have little a over sine of capital A would equal little b over sine of capital B, which equals little c over sine of capital C. And so that's one of the properties that we try and exploit in solving for certain values on the triangle. So if you take a look, we have an example here. We have sine of A equals 1/5, sine of B equals 2/7, and B equals 2/6. Or not 2/6, just 6. So when we look at the formulas that we have right here for law of sines, what can we actually do? Well, we have an angle A, we have an angle B, and then we have a lowercase b, standing for the side opposite the angle B. So we probably want to use the B and sine of B here. And then we want to exploit the fact that we have sine of this capital A. And so that's what we can do. So we'll write sine of capital A right there. And then we'll have little a sitting in that spot. So keeping this in mind, we want to solve for this little a. And our lowercase b is 6. Our sine of b is 2/7. And this should equal lowercase a over sine of A, which is 1/5. Okay, well, how do we go about doing this? Well, in order to solve for A, we multiply both sides by 1/5, and then instead of dividing by 2/7, we can multiply by 7/2, because you multiply by the reciprocal. So we'll take 1/5 times 6 times 7/2 equals A, where it's the lowercase a. And so our final solution here would be A equals, well, just to make life easier, you could cross out that 6 and the 2, you have a 3. So 3 times 7 is 21 all over 5. Okay. If you need to round that to a decimal, that's 4.2, I believe, as well. So both of those are equivalent. So hopefully that makes sense in how we use the law of sines. This one was a little bit nicer. We already gave the sine of A, we already gave what the sine of B is, rather than giving some decimal approximation or just giving the angle and we're supposed to come up with that decimal approximation. But so since we had the fractions, things are nice, and we could work this one out pretty easily in terms of just using that formula. And we have a similar formula that involves cosines. So notice in the case of the sines, we always had one angle in the opposite side along with another side in that previous case, and so we were able to solve that pretty quickly. Now, or I'm sorry, two angles, and one of those angles is opposite. One of the sides lengths that's given is opposite that angle. We'll get in that other case that I just mentioned in a second. So if you look at the law of cosines, though, now you have basically two sides, and then you have the angle that is opposite the angle that, or the side that you're looking for. And that's what this law of cosines is saying. So you have these three little formulas going on right here, but we can figure out all that information just from these pieces. So now if you have, we want to find A, we want to use the formula where we're solving for A squared. Okay, well, A squared equals, well, this should be B squared plus C squared minus 2BC, and then we want to multiply that by the cosine of A. Well, if you look, we don't have A, so we have A squared equals B squared, though, that's 10 squared. C squared, that's 5 squared, minus 2 times 10 times 5 times the cosine of 60 degrees. Okay, so taking a look at this, what do we get? Well, we get b squared, so that 10 squared is 100, plus an extra 25, minus, well, 50 times 2 makes another 100 times cosine of 60 degrees. Well, let's talk about that. Well, we actually will draw a right triangle for this one, just so we can kind of make our calculation. So if you have 60 degrees and you have a right triangle in that case, what does that mean? Well, that means you have a square root of 3 sitting right here, you have a 2 right there, and a 1. And we want the cosine, so that would be 1/2. Okay, so that makes 125 minus 50, and it gives us a final answer of 75. So we can find all the sides, and now if you really wanted to figure out the rest of the triangle, you could use law of, in this case we could use law of sines to finish off the rest. And so we'll go through that in just a second on how to get all of the triangle. That won't be too bad either in terms of what's going on, but we will need a calculator for those parts. This part we don't need a calculator yet. Any questions thus far in terms of the law of sines, law of cosines, and all that jazz? Okay, I don't see any questions, so let's get rocking and rolling. Oh, sorry for the little writing error. I have 30 degrees, 100 degrees, and then I wrote 50 degrees. That was supposed to be a 50 right there. So I do see a question. Let's go back real quick. Why did we do the right triangle again? Well, on right triangles we can figure out values for angles. So the right triangle, what this tells us, is the right triangle that tells us the cosine of 60 degrees equals 1/2. In fact, we could also have the sine of 60 degrees equals the square root of 3 over 2. And in fact, we could do the tangent of 60 degrees just from the right triangle. That's going to be, well, it goes opposite over adjacent, so that's square root of 3 over 1, right, which is just square root of 3. In fact, we could even continue, we could do cotangent of 60 degrees from that right triangle, and that would be 1 over the square root of 3, because it basically is 1 over tangent. And you can get the other values. Secant of 60 degrees would be, that's 1 over cosine of 60 degrees, so that would just be 2. And then cosecant of 60 degrees, that's going to be 1 over the sine of 60 degrees, so that's going to be 2 over the square root of 3. And so basically you can build up every single angle using right triangles. That's what it's there for. But in this case, we don't necessarily have a right triangle in our drawing if we were to ever draw this out. In fact, it doesn't work out to be a right triangle, even though we got 75 as an answer there. Does that make sense then on that one? So that's a great question. Why do we need that right triangle? The main reason is so we can calculate any sort of angle for any trig function that we have. That's what the right triangles work for. Okay. If there's another question, just please let me know. That's exactly what I'm looking for, and that's what I'm here for. So we'll keep on moving along if I don't see any other questions. So that answered it. Awesome. So now looking at this one, final triangle satisfying the given conditions. We have one side is 30 degrees, and actually let me put that back in black real quick just to make sure that we see. So we have a 30 degree angle, we have a 100 degree angle, and then we had this side right here being 50. Now in red we can draw the rest. So I would say in this case the easiest thing to handle is the other angle. So if we called this angle theta, let's say, and we'll fill that in a second. So what we would have is, notice you have 30 degrees plus 100 degrees plus theta, and then we're keeping this in terms of degrees. So it's a triangle, so the sum of all the angles has to equal 180 degrees. Well, that means you have 130 degrees plus theta equals 180 degrees, meaning theta would have to equal 50 degrees. Okay, so looking back at our triangle, now we can fill in that piece of information. If you always have two angles, you should always take care of that last angle. That's the easiest part. So 50 degrees. kind of a coincidence there, the 50 and the 50. Doesn't always happen that way. So now, where can we go from here to get the rest? Well, we need sides. So let's say we want A and we want B. Well, there's a couple ways to go about this. So when you look at, let's say little a, we wanted to work with that. Well, what do we have to do? If we were running little a, notice we have another angle in its opposite side with 100 degrees and 50. So that means we can use law of sines to get little a. And how do we do that? Well, we take 50 over the sine of 100 degrees. And that should equal, well, we should have little a over, what's the angle opposite little a? Well, that's sine of 30 degrees. Okay. So now, moving forward from here, what do we get? Well, you multiply both sides by sine of 30 degrees, so you get sine of 30 degrees times the 50 all over the sine of 100 degrees. And that should equal A. So at the end of the day, we're going to need a calculator for this one. So I'll pull out a calculator if I can find it here. There we go. So we want sine of 30 degrees and all that stuff. So now here's the thing. When you're using a calculator, one thing you need to make note of is what mode you're in. And so when I went into the mode, notice I'm in radians right now, and this is something people, including myself, I've made this mistake a number of times. Oh, is this not letting me? There we go. Okay. So now we have it in degrees. At least I hope. So let's see here if I can clear it up. Alright, good. Okay, so moving forward from here, what do we want to punch in? Well, we want to punch in the sine of 30 degrees. So sine of 30 degrees. So we already have it in terms of degrees. Oops. And so we got sine of 30 degrees. And then we want to multiply by 50. And we want to divide that by our, and I'll put it in parentheses, it's just a good habit to get into, put your whole denominator in parentheses, sine of 100 degrees. So sine of 100. And by the way, we could have figured out the sine of 30. That's not too bad, as a matter of fact. In fact, we just did it basically on the other side. This is going to be 1/2. So we could have just hit 25 times sine of 100. But we'll get the same song and dance, and I'll kind of illustrate that in just a second too. So notice our answer for A is 25.we'll say 39. So A equals 25.39. Okay. Just to illustrate what I said before, 1/2 times 50 is 25. If we hit 25 divided by, oops, let me go back and delete that just to get in the habit. Once again, parentheses. It won't make a difference in this case, but it will in other cases later on down the road. And so I want people to have good practice with it. 25 divided by sine of 100. Notice you get the same answer. Yeah, so 25.39. Yeah, that's awesome. And I apologize for being a little bit slower with this thing. I gotta manually kind of go through and try and get the clicker right on it. But yeah, that's perfect. And just keep on chiming in just like that. That's exactly what we're looking for. So that takes care of that one. So we got that little a equals 25.39. So we can fill that in right here. And so we can put 25.39. So now you actually have options for lowercase b. We could use for 1. We could end up using one option is we could do our law of sines again. If you feel comfortable with that, I'd strongly suggest it. Just to try and illustrate something different, let's try and use law of cosines. So notice that would be that little b squared equals, now we need to take both the sides and square them. So we'll take 50 squared plus this 25.39 squared minus 2 times 50 times 25.39 times cosine of, in this last case, is 50 degrees. Okay, so I know you just saw me work one out where we changed it to degrees. Let me clear this out just to make sure. I'm going to go back to degrees, make sure everything looks hunky-dory. It is in degrees, so we're in good shape. Just a good habit to get into there. So we want to take 50 squared, and then we want to add in the 25.39 squared, so 25.39, and then take that and square it, minus, so let's delete that out. Make sure my symbols line up. 2 times 50 times 25.39, and then times, we had it in degrees, so we're in good shape, cosine of, it's 50 degrees, and don't confuse that with that side that had length 50. That was just a coincidence. And then we hit enter, and we get, whoa, look at that. Oh, I made a mistake actually with A. Oh no, A, I'm sorry, A was good. I might have to go back a page, just give me 1 second here. So B squared equals 1512.61. So B squared equals 1512.61, approximately, I should say. Now, what does that mean? Well, that means B equals the square root of this 1512.61, which we can figure out now. And so from here, there's an easy way to do that. You call upon the second, and we get the square root symbol, which is right above the x squared. And oops, didn't want that little thing. And then we want to click second, and then answer takes the previous line, whatever that output was, and uses it in this line. So that gives us 38.89, which is exactly what we're looking for, 38.89. And that leads me back. I want to go back one page. I got a little ahead of myself, I think. And this is something we can always kind of go back and double check our work. When using the law of cosines, that's the one thing I forget. And there should be a plus or minus possibly, but we dropped the minus because we're talking distance. So 38.89. I want to make sure that I did, yes. So here's the big to-do on the last one where I made a mistake. Notice we had a squared here, a squared. So that's not a box. I shouldn't have that in this spot. I should have a squared equals 75, right? Got a little ahead of myself. My apologies there. So what does that mean? That means a equals the square root of 75, and that's the one we should box. My apologies for that one. So just got to get in the motions of actually trying to do some of these with the calculators to get me thinking that way. But you can kind of see, I think we kind of got a little, we started moving around with the question too. But yeah, at the end of the day, you can get that square root. It's a common error though, is to forget, oh, we have a square initially with a law of cosine, so we got to go back and do the square root of our final answer, as you can see. And so luckily we could solve this and kind of get all those numbers. It's a lot nicer though when we have all the numbers kind of listed. You can kind of get some perspective there. So hopefully that makes sense on that part. And my apologies for that number 2. Okay, so this one's actually really special in terms of the triangle, what's going on here. So we want to find all triangles satisfying the given conditions. So we have A equals 135, B equals 200, and capital A, so the angle A, is about 40 degrees. So you have a couple things going on here, depending upon how this thing's kind of listed out. So if you have, I'm going to draw this triangle 2 different ways. So we have an acute angle with the 40 degree, right? So one option that we can have is, I forget which side I usually put C on, but if this is A right there, we'll have 135 right there, and then B would be something like this, say 200. Right? The other option for this triangle, though, it's not the only option. When you're drawing this triangle, and there's a good reason I didn't draw it out, you can have something that goes like this. And I'm assuming, by the way, that capital B is right here and capital C is right there. So that first one had B as an obtuse. We can have B as an acute angle as well. And how does that work? Well, we can still have the 40 degrees. And we can have the 135 sitting over here just drawn inward, basically. So, and then still have this same distance of 200. So the big difference is we're going to have all three being acute angles, but C is going to be longer in this other case. So you have C sitting right here and capital B. So there's going to be two different triangles that we can get in this sort of scenario. And that's something to pay attention to. So what's the way we can kind of go about that? Well, first things first, let's try and figure out what B is. Now, before we had little a over sine of A and then little b over sine of B. Well, you can flip that upside down and still have the same properties hold. So in this case, what do we have? Well, we can write, we're going to be looking for sine of B. So sine of B over 200 equals, then it would be sine of A, which is 40 degrees, over A, which is 135. So notice this means that sine of B equals 200 times sine of 40 degrees divided by 135. So if we wanted a solution for B, what do we have to do? Well, we have to take the arc sine. So B equals the arc sine of 200 times sine of 40 degrees all over 135 degrees, or not degrees, 135. And so this will give us an answer in terms of degrees too, is the other thing that we're going to be gunning for. So we're going to be trying to get this in terms of degrees. Uh-oh. So let's see if I can pull that back up. There we go. All right. We're back in business. So now we want the arc sine, but first we have to make sure we're in degrees because we want everything in terms of degrees this time. So we have mode. Once again, it's in degrees, so we're good. And now we want arc sine. So we go second arc sine, right? And then we want 200 times the sine of 40 degrees, which will turn it back into just some number, right? So sine of 40, we're okay there. And then divided by the 135. Okay? If we hit enter, notice we get this magical 72 point, we'll say 23 degrees. So B equals 72.23 degrees. But there is some caveat here that we have to watch out for. So remember, you have something like this. In the range of arc sine, was from negative pi over 2 to positive pi over 2. Sorry, including there. And so if you recall, the x value is the cosine theta and the y value equals sine of theta. So we just came up with some angle right here that had a corresponding y value that was correct for us. But notice that also means there should be some angle right here that also has that corresponding y value. So what actually happened is we get two angles for the price of one. And so the case of the acute angle, because it's less than 90 degrees, we have 72.23. And if you go to our right triangle that we create, we know that this angle right here is 72.23 degrees. If this is 180 degrees right here, we subtract those two to get this angle B. So this value would be 180 degrees minus 72.23, right? Which would be, what is that, 107.77, I believe. Double check me on that. 107.77 degrees. That goes in that case. So this is option 1 up here, and this is option 2. So what we found by using the calculator was option 2. And in the case of option 1, we came up with 180 degrees minus 72.23 degrees, which equals, I believe, 107.77 degrees. Okay, so now we've got our angles. We're in good shape. We can figure out C in either case. So in option 2, the angle C should equal, you take the 180 degrees, you're going to subtract 72.23, right, which we already actually know that value. And then we got to also subtract off the 40 degrees, right? So we already knew that this is going to be, this part's 107.77 according to that last piece. And then after that, if we subtract an extra 40, we should get 67.77. So this C value should be 67.77 degrees. So equals 67.77 degrees. And then in option 1, we'll take the C equal to 180 minus 107.77, and then the other angle is 40 degrees, so we'll subtract off the 40 degrees. Well, notice that 180 minus 107.77, that's just going to be 72.23 degrees, and if you subtract off an extra 40 from that, you're going to get 32.23 degrees. So that means that the C in this case is 32.23 degrees. And now you can use either law of sines or cosines, it doesn't matter. We'll stick with law of sines in this case. And so we have the nice one with 40 degrees. We'll kind of work from there. So we'll go with, so we want to figure out this bottom angle, let's call it, or bottom side, that's going to be little c. And so in that case, we'd have little c over, so we're starting with option 2 now, sine of 32.23 degrees equals, well, we can take the 135 and divide that by sine of 40 degrees. So in that case, our little c equals, we would get sine of 32.23 degrees times 135 divided by sine of 40 degrees. Okay, so what does that do for us? Well, let's see here. Once again, check the mode. If I can turn this thing on. Mode, we're back in degrees. Okay, so we're good. We can start punching in the sine. We have 32.23. Close that off, times 135. And we want to divide that by sine of 40 degrees. And so notice we're left with, and there's no reason to do a square root or anything here because we're doing law of sines this time. So C equals 112.00 or 0.01. So C equals 112.01. And so that means that this side right here, where we have the obtuse angle, is 112.01. And so now we have all the values in that case. And then for option, let me put it in blue here. For option 2, we can do the same thing. You get little c over sine of, now it's no longer 32.23 degrees, it's 67.77 degrees. And that should equal still the 135 over the sine of 40 degrees. So that makes C equal to, notice this one should be a little bit larger than the 135 because we have a larger angle involved. So sine of 67.77 degrees times 135 divided by sine of 40 degrees. Okay, bring that calculator up one last time. And what do we get? Well, we get sine of 67, and I should have checked for degrees, but you can push the I believe button at this point. I've done it enough times where hopefully you can see what's going on. Times 135, and then divided by our sine of 40 degrees. And we get a larger number, which is what we expected, 194.41. So this is approximately 194.41. That allows us to change this C to 194.41. So just be aware. Notice what we began with, right? We began with two angles open, and then you had an angle in its opposite one, its opposite side, and then just one other side. That allowed for some freedom, enough freedom for us to kind of work and get two different triangles that work out. Okay, so keep that in mind with what happens on homeworks and stuff. So there will be those occasions where you have to use both. So now we're done with law of sines and law of cosines, and whatnot. So let me get back to the. There we go. So now what we want to try and do is work with trig identities. And the biggest trick to trig identities is breaking things down in terms of just sines and cosines. If you can do that, you're going to be in great shape a majority of the time. So with that in mind, we have sine squared of x, cotangent squared. Well, that is cosine of x over sine of x, but so since it's squared in both positions, so you have cosine squared over sine squared of x. And in terms of these trig identities, I'm just saying try and find something that has less than the number of elements there, or number of trig functions there. There's different ways. Sometimes you'll see a list of them and they'll say figure out which ones work and stuff like that. But it's the same old song and dance. So tangent, we can write as sine over cosine. So since it's squared, you're going to square both pieces. And let's check out what happens. So this whole thing, we have the sine squareds cancel, and then we have the cosine squareds cancel. Alright, so what we're left with is cosine squared x plus sine squared x, which does have less terms. But if you really wanted to make it less, you might recognize that identity. Sine squared x plus cosine squared x always equals, and you can plug in any angle you want for x, always equals 1. And so once we have that, we're done. Bada boom, bada bing. And you can't get any better than just a constant for our answer. So all that junk right there just simplifies to 1. And that's a trig identity. So you can see the power of just manipulating sines and cosines. I mean, it breaks apart very nicely, fairly quickly too. So in this one, we aren't going to be able to, so you have cosine of x plus cosine of y, sine of x plus sine of y. As written, we aren't going to be able to break that down much. Okay, so what we should probably do, we're squaring both of these, so let's think back. First off, you need to remember how to square things. So you have a plus b, the quantity squared, that's a squared plus 2ab. That's the thing that most people forget about. at 2ab sitting right there, plus b squared. Okay, we want to reduce the number of trig functions involved. So this might look a little more complicated. It might seem like we're heading in the wrong direction at first. So we have cosine squared of x plus 2 times the product of the two terms. So you got 2 cosine of x cosine of y plus cosine squared of y. So this whole thing equals this. And then plus, so this is the first bit, and I'll just put it in parentheses so we can distinguish between the two. And then we're going to do the same thing for the second two involving the sines. So you have sine squared of x plus 2 sine of x sine of y plus sine squared of y. Alright, so now let's start doing some regrouping. First off, I see a cosine squared and a sine squared. I'm going to group those two things together. Then we can group the sine squareds of y and the cosine squared of y. And then the remaining piece, we'll kind of group that together. So first off, cosine squared x plus sine squared x. So notice both of those will have the same angle. And hopefully you can recognize that from just one slide before here. And then the same thing, we want cosine squared of y plus sine squared of y. And then the other piece, notice we can write the rest as 2 cosine x cosine y plus 2 sine of x sine of y. So notice that first whole term, that whole thing just goes to 1. The second term just goes to 1. This third term we're going to write a little different. So you get plus 2 times, we have cosine of x cosine y, we factored out the 2 there, and then we have plus sine of x sine of y. So notice 1 plus 1 is 2 plus 2, and then I don't know if you do recognize it or not, but notice we have the sum of cosine of one angle, cosine of another angle, and then sine of an angle along with its other angle that corresponded with the cosines. There's a magical way we can write that, and if you remember from your difference formulas that you had before, this is just cosine of x minus y. Okay? So you can write it, there's a few ways you can have this written. One is like 2, and then you can write 1 plus cosine of x minus y. Or 2 plus 2 cosine of x minus y. That can do it. Sometimes you might see this line before be a finishing point. But I just want you to be aware that, hey, we can really limit this down. Notice we only have one trig function once again. It's just a matter of knowing your identities, like what you have. If you know your double angle formulas, your half angle formulas, your sum and difference formulas, and all that stuff, you're going to be in great shape come test time. And basically making sure you can write things in terms of sine and cosine. That's the big to-do on these. So on our next one, when we're working with this thing, I'm going to write a little note down below. Sine of 2x, we have a double angle formula, or you can use the sine of x plus x. That will get you there too. But so you get, this is 2 sine of x cosine x. Okay, yippee-ki-yay, right? And so our other one is cosine of 2x. And so what the heck does that equal? Well, that's cosine squared x minus sine squared x. Okay, so the first one we did, remember we had tangents, cotangents, we wrote everything in terms of sine and cosine. Now when we have a double angle inside, we're trying to break it down in terms of sine and cosine just once more. Okay, so this whole thing becomes 2 sine of x cosine of x all over 1 plus, we just said cosine of 2x is cosine squared x minus sine squared x. Not to be confused with cosine squared x plus sine squared x. We do know that sine squared x plus cosine squared x equals 1. So what that tells us is that cosine squared x also equals 1 minus sine squared of x. So write this is this whole thing equals 2 sine of x cosine x over the fun part, this is 1 minus sine squared x plus a cosine squared x. So what the heck does that equal, right? Well, notice you have 2 sine of x cosine x. 1 minus sine squared x is just cosine squared x. We just wrote that down below. Plus another cosine squared x. Well, you have a cosine squared x plus another cosine squared x. That makes 2 cosine squared of x down below. So we can rewrite this as 2 cosine squared of x. So that's a lot of work, but now we can cross off the 2's. Right? And what seemed like we had something very simple with just 2 trig functions. How are we going to get it down to 1? Right? We seem to be getting more and more complicated, but this cosine of x will cross off that square, and what we're left with is just sine of x over cosine of x. And hopefully you can recognize what trig function that is. A much simpler format to write that is just tangent of x. So all of this work, we've gotten down to this whole thing is just tangent of x is our solution. We got one trig function, so that's exactly what we're gunning for. And so notice each time we were getting it down to kind of one main trig function and we were good to go. Alright, so trig equations is kind of our next little shindig. And let's see if we can finish this thing off here. So we have 3 sine of theta minus 1 equals 0. In this case, it's like a linear equation, right? So what you can do, if you don't like the trig functions, you can set u equal to sine of theta. Then notice you have 3u minus 1 equals 0, right? So it's just a substitution if you want to do that. Then, so if I said solve for u, hopefully you can do that. You get 3u equals 1, so u equals 1/3. But if you remember, u is just sine of theta, so you get sine of theta equals 1/3. So some people that helps, some people it doesn't. It doesn't make sure. So I see the wow. Hopefully that might have been in reference to the whole thing boiling down to just tangent. Yeah. So all that work we get down to tangent and whatnot. So moving forward to this, and if you have any questions, as I said, just keep them coming. Let me know, and I'm happy to refer back. So how do we get rid of the sine of theta? Well, we take the arc sine of both sides, and it kind of cancels out with that left-hand side. So you get theta equals the arc sine of 1/3. Now, I have no idea. Well, I have a kind of an idea, but I can't be exact with arc sine of 1/3 off the top of my head. Now, the other thing, too, we're going between 0 and 2 pi, so that's telling us we're in radians now. So the fun stuff has just begun. So our mode, whoops, this thing, there we go. We want to switch to radians. Oh, come on. There we go. So now when we go over here, click enter, we're back in radians. Awesome. And so where do we go from here? Well, we got radians. Now we want to find the arc sine. So second arc sine of 1 divided by 3. And I'm sure this is going to be the number you're thinking of, right? 0.33. Now, just to give you an idea, remember we go back to our unit circle. So this is a, well, let me write it out. 0.3398. So this is approximately 0.3398. Right. Remember, x equals cosine theta, y equals sine theta. So we just came up with some angle 0.3398. Now where the heck does that fall? We want to get all the way between 0 and 2 pi. So first things first, pi over 2, that's like, you can say 3.14 over 2, but notice that's essentially, it's going to be slightly bigger than 1.5, right? And we have 0. So 0.33, it's some angle right here, right? So if we're looking for all the angles in terms of what happens, that means this is, we're looking at this y value. Well, where on the circle can give you that y value? Well, it would also be right here, meaning that this angle is also 0.3398 radians. Okay, so our theta for our solution, we have one theta is 0.3398, and then the other theta, the easy way to take care of that, notice it's going to be pi, and we're taking away the 0.3398 to move back, right, to go kind of counterclockwise. And those are the only two values that give you that y value that we're looking for, of 1/3. And so those are your final solutions within this interval. Questions on that one? These can be really tricky in terms of seeing, hey, we're going to have a couple things happen in there, but always go back to the unit circle. It helps tremendously in terms of seeing, okay, if you know that the x value is the cosine theta, the y value is the sine theta, you can kind of break it down from there, right? So I don't see any questions at this point. We'll kind of move forward. If there are questions, let me know. So now on this one, if you don't like working with the trig functions, once again, let's just use a u substitution, or you can call it an x or whatever if there's thetas involved. I just like u because usually you don't see a cosine of u or things like that too often. So this is, if we say u equals cosine of theta, notice we have 2u squared essentially plus 5u equals 2. Well, this is just a quadratic, and so, oh, -2, my apologies. So you get 2u squared plus 5u, you add that 2 to the other side, and hopefully we can factor. I make no guarantees though. So if we're able to factor, let's see here, we'll have a 2u here, and that means we'll have a u there, and we need it to be positive and positive. Oh, okay, so this one will work out pretty nicely. So we have 2u plus 1, and then u plus 2, and this whole thing equals 0. Okay, well, we can plug, well, we can set each of these equal to 0. We'll do that way. And then we have u plus 2 equals 0. So notice in this case, I'll write it up here, we have 2u equals -1, or u equals -1/2. Okay. In the other case, you have u equals -2. So now plugging the cosine of theta back in for u, you get cosine of theta equals -1/2. Okay. And the other one would be, that's going to be where cosine of theta equals -2. Now one of these is pretty easy in terms of whether or not what your solution is. Solution, I guess, is what I was trying to say. So you have, once again, 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okie dokie, but notice all these max out. On our unit circle, you have 1, you have -1 for the cosine as far as you can get to the left. So that means there is no solution for that thing right there. Okay, the nice part on this, you could use your calculator and all that, but actually this one we can avoid it altogether. So notice these are the two spots where cosine theta is less than 0. So we know we're going to be in those quadrants. So we'll just figure it out from there after we can work with this triangle here. So if we put cosine of theta, so if we put theta in here, let me put theta sub 1 actually, so just to indicate a different, slightly different theta. So what happens is we have 1 down here and we have 2 right here. That means this is square root of 3. So that means that this should be a 60-degree angle, or pi over 3. So what we have, if we're looking for those x values, we have something like this, where this is pi over 3, and this angle as well, because this would be the same x value down below, and so this should also be a distance pi over 3 from that pi spot. Well, so notice we have two angles that can satisfy this, and the reason why we put them in that quadrant, we want the cosine value to be negative, so it all boils back down to that unit circle. So theta equals, well, one solution, since we're between 0 and 2 pi, you go pi minus pi over 3, and the other one is pi plus pi over 3. So the first solution was 2 pi over 3, and the second solution is 4 pi over 3. And notice we did that one without a calculator, so you can have some fun too every now and then. Questions on that piece? So hopefully you're seeing how when we're between 0 and 2 pi, we're getting at least a couple answers going on there. Alright, so we'll bring it home with this one. We have sine 2 theta minus cosine theta equals 0. Now one move people do is they'll move the cosine theta over to the other side. What I'd recommend though in this case, you have a 2 theta on one for an angle and a theta on the other. So let's use a trig identity. And the big one is what sine 2 theta equals. Well, that's 2 sine of theta cosine of theta. And then we can go minus cosine theta. So this one might be a little bit trickier, because how do we handle this with two trig functions? Well, notice a cosine theta is in common with both of those. So cosine theta you can factor out, and you're left with 2 sine of theta minus 1. Hey, what do you know? So this one I'll avoid actually doing substitutions, because we're pretty much right there. So you get cosine theta equals 0, and then you have 2 sine of theta minus 1 equals 0. Well, when does cosine theta equal 0? Well, we'll go back to the unit circle once more. Remember that x equals the cosine theta, and y equals the sine of theta, where you have 0, pi over 2, pi, and 3 pi over 2, and then we're always staying between 0 and 2 pi in these cases, right? Just want to make sure. If it's not, we got to do some extra work. You can look at my old review session to show you how you can generalize all this too. So between 0 and 2 pi, what happens? Well, pi over 2, notice the x value equals 0 at this point and at this point. So you have 0 for the x, and you have 1 and negative 1 for the corresponding y, but we only care about the x for cosine theta to equal 0. So that means that solutions to this are theta equals pi over 2 and 3 pi over 2, and we're done with that. For the other component, you see 2 sine of theta equals 1, and so that means sine of theta equals 1/2. So notice where that would occur, that's going to be, we want the y value to be positive, so you need some angle going right here and some angle going right there, right? So that's where the sine of theta is going to be 1/2. And so we need to figure out what this angle is. But remember, if we have sine of theta equal to 1/2, we can go back to the right triangle again. So if you have 1 here, if this is, and I'll call this theta 1 because we have two angles going on here, and you get a 2 there, that means square root of 3 goes down below. So what does that mean about theta 1? Well, theta 1 must be a 30-degree angle, which is pi over 6. Okay, so the one angle is probably the easiest one we dealt with, is pi over 6, right? So you get pi over 6 for that first case. But notice the other case, we got to take pi over 6 away from pi. So you go pi minus pi over 6. So what does that make? Well, that's 6 pi over 6 minus pi over 6. It's going to be 5 pi over 6. So theta equals pi over 6, and then 5 pi over 6. And ta-da! We have our final solution. So we have 4 answers. So you have theta equals pi over 2, 3 pi over 2, pi over 6, and finally 5 pi over 6. And that's our final answer. Okay, any questions on that last piece? So hopefully you can see a few more. I mean, and the biggest thing is just keep on practicing all these, right? If you practice law of sines, law of cosines, if you practice the trig equations and trying to work these out, noticing multiple times we've come up with 2 solutions at a time when we have our triangles involved and using our unit circle. We're kind of piecing all that together with these trig equations. So if you keep that in mind and keep on practicing, it does help out tremendously. That's the biggest thing. Practice, practice, and more practice. So I don't see any questions. So I'll hope all goes well, and then you have a good weekend. So talk to you later, and I'll see you at the next review.